So we just heard from Gaetano how to encode integers and floats. And now in this new section, we're going to start looking at machine code. Okay, so by machine code, if you recall, we saw in the first section, are these zeros and ones that tell the computer what to do when executing a program. Okay, and that's gonna, we're also going to start looking at an introduction to assembly language and what you have to understand in terms of basic machine organization in order to learn about assembly programming and learn how a computer works down a little bit lower level. Okay, so here's what we're going to see in this section. We're going to see what an instruction set architecture is, which is the hardware-software interface. It's the contract between hardware and software. We're going to look briefly at the history of Intel processors and architectures, and then we're going to see how C and assembly code and machine code relates, and it's going to start looking at x86 basics. So we saw this picture in the very first section, and if you recall, this is the lifetime. The lifetime of a program starts with coding time when you write the code, compile time when you translate from the high-level language all the way down to machine code, the zeros and ones that compose what the computer understands, okay, and then runtime, which happens when you actually executing the program. Okay? And also recall that what makes programs fast is, well, your algorithm, how you write your code, okay? What the compiler does, in other words, how the compiler translates from C code to the hardware-software interface, to the ISA, the instructions that are chosen by the compiler, and then the assembler converts that to zeros and ones, to machine code, and then, you know, depending on how the hardware executes it, it's going to make your program run faster. Okay. So just to repeat what I just said, you know, the time required to execute a program depends, well, in the program itself, what algorithm you've used, how the compiler translates that code written by the programmer into assembly instructions. It also depends on the instruction set architecture, which is a set of basic instructions offered by the processor to the compiler or to whoever is writing assembly code. And then ultimately, of course, the program performance is also a function of the actual hardware implementation. How the hardware itself is organized to execute those instructions. Okay, so now let's spend a little bit more time understanding exactly what the ISA is. Okay, so the ISA defines three important things. The first one is the system state. What defines the state of your system? Okay, of your computer system. That includes the contents of registers, which is, as Gaetano told you, a basic unit of storage inside the CPU itself. Okay, it includes the program counter, which tells what instructions being executed at that time in the processor, and also it includes all of the contents of memory, everything that's stored in registers, memory, and including the program counter is part of the system state. Okay. So the ISA also defines the instructions that you execute, that the CPU can execute at the most basic level. Think of that as very, very simple instructions, things that do like an add or a subtraction or, say, a load from memory. Okay, that gets data from memory into a register as another example of an instruction. Okay. And finally, the ISA also defines what exactly happens when these instructions are executed. Because when one of these basic instructions are executed, it changes the state of your computer system. Okay. So, and how this state changes is also function of what the ISA specifies. Okay. So here are the major decisions when designing an ISA. First, well, obviously, what instructions are available, like add, subtract, multiplication, floating point operations, and so on. Okay, and what do they do? Exactly how they change the system state, and also how they are encoded. Because if you recall, when, say, you have an add instruction in assembly, it becomes some sequences of zeros and ones. That's what the computer actually understands. And the encoding is exactly this mapping between the instruction in the ISA and the actual bit sequence that determines that that encodes that instruction. So the ISA also tells how many registers your computer has, how many explicit units of storage you have inside your processor. Okay, so how many you have available, and also how wide they are. Right? For example, are they 32 bits? Are they 64 bits? or are they smaller, like in case of very simple processors, and so on. Okay? And finally, the ISA also defines something very important, which is how do you specify a location in memory? Okay, so how do you specify an address in your assembly code, or how in your instructions? Okay, how do you tell instructions what addresses they should be manipulating? Okay, it's also called, what are the addressing modes supported? Okay, so let me write it here: addressing modes. All the ways that you can specify an instruction in an address in your program. So now, x86 is one type of ISA. Okay, so it's very, very popular. Okay, so that's and in fact it's so popular that x86, which is you probably know Intel. Intel Corporation makes x86 processors, or processors that implement the x86 ISA, and these processors completely dominate the server, desktop, and laptop markets for now. And they actually had a very evolutionary design. Now, in fact, if you have code written for the 8086, all the way when it was designed in 1978, in fact, very close to when I was born, so code written for the 8086 still runs in the most modern Intel x86 processors. Okay, so it had very, very evolutionary design, and more features were added as time went on. And x86 ISA is something that is a type of ISA that we call CISC, which stands for Complex Instruction Set Computer. Okay, what that said is that the basic instructions specified by the x86 ISA are very rich. Okay, they can do things like, move a string in memory. They do things that are much more basic than just a simple add, a subtraction, or move a little bit of data here and there. It does things that are much richer than that. Okay. So, and we call it CISC, as in Complex Instruction Set Computer, as opposed to RISC, which stands for Reduced Instruction Set Computers. Okay, a RISC machine has much fewer instructions, and instructions are much, much simpler. Okay, so in more advanced computer architecture courses, you see that this has a lot of implications on how the hardware itself is designed. Okay, but it's a little bit out of the scope of this class to give you the details of whether an ISA being RISC or CISC, why and how it affects computer design. So let's look at some numbers here just to give an idea of how amazing this evolution was. Okay, so if you go back to 1978 when the 886 was introduced, that processor had 29,000 transistors, and it ran on between 5 and 10 megahertz. That's the cycle time of the processor, between 5 and 10 million cycles per second. Okay, at that time there was the first 16-bit processor. That means that the word size was 16 bits or 2 bytes, and it was the basis for the IBM PC and DOS that really popularized personal computing. That's a very, very important processor. And the total address space, the maximum memory you could address was 1 megabyte. Can you imagine that? It can't even hold a photograph. But and then another major step was that the 386 that was introduced 7 years later in 1985, and it had 10 times as many transistors. It ran about 3 times faster in terms of its clock frequency, but it was significant for a number of things. Okay, it was the first 32-bit microprocessor. Okay, it was referred to as the IA32. It had a flat addressing mode, meaning that you didn't have to divide the memory into regions called segments and address them individually. You had a single address that could point anywhere in memory, so that made the process of managing memory and accessing memory much, much simpler. Okay, so and this machine is also capable of running an operating system called Unix, which is very similar to what we call Linux today. Okay, and so it's very similar. Linux is a type of Unix operating system. Okay, and today 32-bit Linux GCC targets the 386 by default. So 386 is a very, very important architecture as well. Now let's jump 20 years later and look at what happened. Now the Pentium 4, when it was introduced in 2005, had 230 million instructions. We're talking about a 10,000 fold increase in the number of transistors. Okay, and about a huge increase in frequency as well. Okay, and then the Pentium 4F was the first 64-bit processor, also introduced by first 64-bit x86 processor introduced by Intel. This is also referred to x86 x86-64, and AMD was actually involved in defining what the x86-64 looks like as well, which we're going to see in a second. Okay, so just a little bit more history of Intel processors. The 486 was introduced in 1989. Was also a very important processor. Then there was a series of Pentium processors that had a lot of evolutions, including like around this time, they were starting to worry about power consumption as well. So, and then there was a Core 2 Duo, which was a dual core processor. Processor had multiple compute cores in the same chip. And then more recently, we had the i7 that, for example, here we have a die picture. There's a picture of the actual silicon of the i7, and this had 4 cores. See, this is essentially, these are exactly, each one of these boxes here, okay, are, each one of these boxes is a processor, and you have 4 of them on a chip, and they all share a bunch of cache memory that we're going to see exactly what that means in later sections of this class. Okay, so, and along this history, there's a lot of other things that were introduced along the way. One was support for multimedia operations. It's essentially, multimedia operations tend to have a lot of fine-grained parallelism at the instruction level. We call that vector type of parallelism. So, and in order to take advantage of that, Intel introduced an extension to its ISA called SIMD, which stands for Single Instruction Multiple Data. And that instruction actually operates in multiple data items simultaneously, so taking advantage of parallelism that the application has. Okay, so and also along this way, like in this ISA evolution, not only ISA and architecture evolution, there were instructions that were introduced to do more efficient conditional operations. Okay, we'll see later in this class that there's these instructions called branches that changes the flow of execution of the processor, and these instructions can be very, very expensive. So, and part of the innovation that happens in this evolution of microprocessor was to make some of that much cheaper. And then obviously, as I mentioned before, there are lots of cores introduced along the way. Okay, so if you're interested in learning more about the specifics of Intel's architecture, you can go to the Automated Relational Knowledge Base, great name, that's available in Intel websites. And also, you can look at the list of Intel microprocessors on Wikipedia, which is great to get more historical information as well. But now let's not forget about AMD, a company called Advanced Micro Devices that made clones of x86. By clones, it means that other processors that had a completely different hardware, but also implemented the same instruction set architecture. That's one example of the beauty of abstractions. Since you had the same abstraction called the instruction set architecture, the hardware-software interface was the same, the implementation underneath doesn't really affect software as long as the ISA stays the same. And so AMD came up with completely different hardware that implemented the x86 ISA, and it had some advantage. At first, they were a lot cheaper, it was a tiny bit slower, but it made sense in terms of price performance. Okay, typically it just followed behind Intel, but then AMD got really, really aggressive in terms of taking advantage of new circuit design techniques, and they designed very, very, very fast processors. And one great example is the AMD Opteron, which is really, really tough competitor to the Pentium 4. And AMD was also instrumental in developing the x86-64, which is the 64-bit extension of the x86 ISA that later on actually became a good part of what the x86-64 looks today, even for Intel processors. Okay, that's really, really interesting, quote-unquote collaboration between two companies that are essentially competitors. Okay, so now to end this first module of this section, just to tell, we are going to cover now this section in x86 programming, which will be the following section. We're going to look at what's called IA32. It's the traditional 32-bit ISA, and let me fix my 3 here, 32-bit ISA, and then we're also going to talk about the 64-bit version of the x86 ISA. Okay, and keep in mind that all lab assignments are actually going to use x86-64, but when teaching you assembly programming, it's going to be largely transparent to you. You're going to know when it matters. Okay, thank you and see you soon.